Yes, I want to save the recording. All right, so 6.2 means, averages, confidence interval, standard error is this magic number called t divided by the square root of the sample size. What is t? Well, t is like z. So t is like a z-score. But instead of coming from the normal distribution, it comes from a t distribution. That is the square root of n down there, correct? Yeah. So like z, but from a t distribution. Sometimes it's called the student's t distribution, and it's not student like I'm a college student or high school student. There was a guy named Student, and he came up with this idea, and everyone agreed, oh yeah, this is a better idea than using z-scores. And I'll talk more about why later. So we use z-scores. So now with the central limit theorem, we're going to use z-scores every time we have a proportion, but we'll use t-scores every time we have a mean. Is the difference. And like a z depends on the center and the standard deviation. A t-score only depends on the sample size. A z-score is for proportions, and from now on, a t-score is going to be for means. Oops, depends, there we go, on the sample size. A new term related to the sample size is called the degrees of freedom. Is always the sample size minus 1. And if you want to know why it's n minus 1, then sit down for a cup of tea with me after class and we'll talk about it. That's all we need to know for now. All right, so that's for a confidence interval. For a, otherwise everything's the same. We just have a way to predict what the standard error is now. So zoom, 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 zoom. For a hypothesis test, hypothesis test, thesis, there we go. We're going to calculate not a z-score, but a t-score. And it turns out a t-score looks just like a z-score. You take whatever the sample says, you subtract whatever the null hypothesis says, and you divide by the standard error. So it looks just like a z-score, but we call it a t-score. Oh, something's wrong there. That's not supposed to be a t there. I can't put t in both places. That's illegal in statistics, not in algebra. That is supposed to be an S. Sorry about that. What is S? Standard deviation of the population or the sample? The sample, yes. Okay, so reminder, S is the sample standard deviation. Sample STD. Okay, so it's not really much different than before. We're calling them t-scores, and in some sense, it's just a new name, but it is a slightly different calculation. So if I jump over to stat key, where's my stat key? Over here. They have a theoretical t right next to the normal. So if I'm doing a mean, I just go there instead. Now, again, when I do use the theoretical normal, it's if I have a mean of 0 and a standard deviation of 1, what kind of normal distribution is that one? Anybody recall? There's 2 ways you can name it. If the mean is 0 and the standard deviation is 1, it is either called the standard deviation, the standard normal distribution, or it is the distribution for z-scores. What? Z-scores, yes, it's the distribution for z-scores. Yeah, so a normal distribution with a mean of 0 and a standard deviation of 1 is a distribution for z-scores. All right, let's go over to t. When you do t, it immediately says, hey, what's your degrees of freedom? Degrees of freedom is always sample size minus 1. So we're going to need a sample size in just a minute. We'll get that. So we'll come back there. On my spreadsheet here, zoom out for a sec. Confidence interval for a mean I have here. So that's the third tab over. And notice I start switching to t's. And it uses a thing instead of the norm and the norm inverse to make calculations, it uses the t and the t inverse to make calculations. So the spreadsheet's already set up to use t. Same thing for the hypothesis test. As far as a hypothesis test, we have two different situations. One situation is where somebody just says, hey, I have the sample. It's got a mean of blah and a standard deviation of blah. What can you tell me about it? Otherwise, I have all of the original data. And so there's two different tabs depending on whether the problem gave you just the summary statistics or whether the problem just gave you the original data. So you have to decide there. Kyra, you had a question? Okay, the spreadsheet, if you didn't make your own copy last time, is on the week 8 videos and more. At the very bottom, it says sample spreadsheet with tabs for each type of situation. And you can just grab that, it's a Google Sheet. And so if I just open it up in an incognito window, if you're signed into Google, it will allow you to make a copy. If you're not a Google user, then download it as an Excel sheet and then use it as Excel. It works just fine in Excel. All right, cool. All right, let's do something. So we are going to take a look at what you guys told me about TV in a couple of different ways. First, I'm going to grab your TV data from the beginning of the quarter. TV hours 2022. All right, here we go. So this quarter, I had, how many students fill this out? I had 33 students tell me how much TV they watched. And that was the same question you saw earlier in the class. So the question was related to this right here. How much TV do you watch on average per day? And include like recorded videos, streaming services, games, include time when you're not fully paying attention. Like my daughter likes to watch Criminal Minds while she's making pasta in the kitchen, which I think is dangerous for many reasons. But not if there's like a TV somewhere else in the house on. Like I go to my sister's house and she always has Fox News blaring in the living room all day long. It is, yeah. I don't know how she does that. She just likes the background noise. It's better than the noise outside, I guess. And when we were talking about this earlier, I wasn't like, nowadays we watch a ton of videos for school. I wasn't counting that. I was thinking this as recreational. So maybe I need to amend this question in the days of COVID where we watch way more videos for school than we used to. All right, anyway, so here's the information I got. What do I need to know from this? So I'm just going to do some standard summary statistics real quick. Summary, we would like the count N, we would like the mean X bar, and according to the, what do you call it? Central limit theorem, we also need the standard deviation, S. I'm going to call that STD. All right. And do I really need to recreate a spreadsheet with all this stuff in it? No, I already made one that does it, right? All I have to do is grab this data and plug it in there. Now, oh, you guys don't have this data though, do you? That's okay. You just need the summary, unless anyone really wants it. Does anybody really want it? No. Okay, if you do, just say and I'll send it to you. Copy, and then where's my spreadsheet? Okay, which tab do I want? Let's see. Yeah, confidence interval mean with data here. So I'm going to get rid of the husband and wife, and this is TV time. That is an interesting study though. So TV time per day. I guess I should be more specific. It's hours per day. And then I want to make sure I delete everything here. Got it. All right, and then I can paste my stuff in. And then the spreadsheet just calculates everything I need. So I can see the sample size is 33. I can see X bar, the mean is about 2.4. I can see the standard deviation is about 1.7. So for this group of 33 students, what I can say is, well, on average, people watch around 2.4 hours per day. And there's a spread of about almost 2 hours per day with that. So I could say like 95% of these students watch somewhere between, what would that be, like 2, 3, 4.5 to a half an hour a day. based on this information here. If I use that 95% rule, 2 standard deviations from the mean. It calculates the standard error for me. I'm having a 95% confidence interval, which is pretty typical. It calculates the t-score I need. Now, does the t-score depend on the, let's see. Yeah, the t-score does depend on the confidence level. So let's go over to StatKey and check this out for a second. So if I look at StatKey, let's see, if I have a sample size of 33, the degrees of freedom would be 32. So I just type in 32 there, hit enter. Now it's kind of like a normal distribution or standard normal. I just pick what percent I want in the middle. And I'm going for 95. And StatKey says the t-score for a sample size of 33, which has 32 degrees of freedom, would be 2.037 to 3 decimal places. Did my spreadsheet agree with that? 2.0369. Yeah, if I rounded that down to 3 decimal places, blow that up a touch. Whoa, a little too much maybe. All right. All right, so what do we know? For a 95% confidence level, our prediction for the hours of TV college students watch is between 1.8 and 3.0. If I went to 1 decimal place hours. So I think college students watch somewhere between 1.8 and 3 hours per day. All right, so let's back up just a second. Do I have a good representative random sample? No, these are people taking statistics from me, Gary Parker at BMCC in 2022 of the spring. That's a pretty biased sample. Right, people happen to be taking this from BMCC. I happen to be the only teacher. You're all here for a specific reason. I'm not exactly sure what those are, but there's a lot of things that lead this to probably not be a representative sample. Next problem is what? Thinking way back to like week 1, somebody brought this up earlier today, self-reporting. You're telling me what you think it is, and you might underestimate because you're like, ooh, I don't want them to think I watch too much TV and I'm not paying attention to my classes. So I'm gonna say I only watch 3, even though it's more like 7. Okay, so this is not a representative sample, so I really shouldn't go by it, but it's some data from you guys, and maybe you underreported. Okay, so I don't know. Based on the survey I asked earlier, when I asked you to think about in general, how much do college students watch a day on average, it looked like 4 was around in the middle there. Okay, so is 4 in this interval? No, it's not in this interval. Okay, so do these college students seem to watch less than what we think the national average is? Since 4 is what we're guessing at the national average isn't in this interval is below 4 entirely, right? It goes from 1 to 3 or 2 to 3, basically. We're thinking, oh, interesting. These students seem to watch less than what we thought in general. So again, your thoughts in general are back here, here, here. There we go, zoom out. So based on that survey, people thought somewhere, oh, that's weird. Why is there a 5 way over here? And then it goes 1, 2, 2.5. Oh, there's 2 4s. Oh, I know why. When people fill out the survey, they might have typed 4 with a space after, and then the computer will see it differently as just a 4 on its own, right? Because notice they counted all of these 3s in one spot, but 3 4s are here and only 1 of them were here. So that means somebody typed that 4 a little bit different than other people typed this 4. And generally, like I do this sometimes, I hit space key all the time when I'm typing, and I might accidentally hit it when I'm typing something. So I got to scrub the data to clean it up. But anyway, it looks like it's around, 3 is what people were predicting here. 3 is more in the middle, isn't it? Maybe we should go get people's responses and take a look. So Google also gives me a spreadsheet version of this. So let's take a look at the spreadsheet. And my guess is some people type spaces in here. Not there. Not there. Let's see. It was the 4s that were kind of weird. Not there. Huh. I don't know why it treated the 4s different, and it treated There's a 0.5. I thought there were 2 5s. Oh, that's a 0.5 without a 0. Oh, okay, I see. I didn't see the point. It's so tiny. All right, so it's that one right there. All right, so if we average these up, so let me just duplicate this and see what people thought on average. So there's the copy. So on average, our prediction for the national average is about 3. Oh, okay. 3 is in our interval, isn't it? Okay, this one's 3.06. And then our interval, where'd it go? Oop, is 3.01. It's a little bit outside. Okay. So is the average for this group of 33 people significantly less than our prediction for the national average? Okay, Andrew says, no, I don't know until I run the hypothesis test and see. So we'll have to do that. All right, let's draw a quick picture and then we'll do a hypothesis test. So we're applying what the central limit theorem says. We'll also check on StatKey, see what StatKey says about it with a simulation. So this is the average hours per day of TV time. And our confidence interval had a mean of, what did that spreadsheet say? 2.4-ish. So the sample data, X bar goes in the middle, that was about 2.4. We are going for what we call a 95% confidence interval. And the endpoints, let's just go to, I guess I go to 2 decimal places, 1.81 and 3.02. 1.81, 3.02. 1.81 and 3.82 is our spread there, and our margin of error, according to the spreadsheet, let's blow that up a little bit more, was about 0.60, 0.6 to 2 decimal places. And these are all hours per day, as I labeled above right there. So we're 95% confident that the average amount of TV that college students watch is somewhere between 1.81 hours and 3.82 hours. Did I get that right? No, it's not 3.82, it's 3.02. Oops, thank you. Come on. My eraser has been finicky lately. Maybe my pen needs a new tip. 3.02, okay. So let's write that statement. We are 95% confident that the average hours per day of TV that college students watch, however you want to word that, is between 1.81 and 3.02 hours. And again, there's many ways to word that, but you want 95% confidence in there. You want to make sure you get the right group and the right units and what those upper and lower values are. Now, I am just curious as to what StatKey would do with this. You can only use StatKey if you have the original data, which I happen to have. And since I didn't send you the data, you're going to have to just watch me do it. So I'm just going to copy this into a StatKey. Let's see, what are we doing? We're doing confidence interval for a mean. And then I just replace their data. Oops. Oh, okay, and I'm pretty sure I did not get the header, is that right? Yep, so uncheck, okay. So there's my mean of 2.41, blah, blah, blah. And I just generate thousands of samples. And StatKey should give me a similar standard error and a similar interval. Do I have a big enough sample to do this? Anybody remember the cutoff on sample size for, ooh, I got 10,000. Anybody remember the cutoff on sample size for using the central limit theorem? 30, yeah. If your sample size is over 30, it's okay to use the central limit theorem. The bigger the sample size is, the closer the simulation will be to what the prediction will be. So here I have a standard error of 0.292. The spreadsheet thought the standard error was 0.296. They're in the ballpark of each other. 292, 296. And this is a confidence interval, so we always select two-tail for confidence interval. And we're using the standard 95 in the middle. And StatKey says it's about 1.9 hours to about 3.05 hours. Is that the same as what we found? No. Is it similar to what we found? Yes. Okay. All right, so StatKey agrees with the prediction from the central limit theorem formula, which is kind of cool. That weird square root formula agrees with this crazy computer simulation. This blew my mind when I first saw this. But keep this in mind, there's a lot of things in math that didn't blow my mind till like years later when somebody brought it up again. Did you know you can calculate this in calculus? It's like, what? Oh my gosh, they didn't teach me that in class. They tried to, I just didn't get it at the time. All right, we're gonna do a hypothesis test next, but I am gonna split the video.